This video is all about the differential media used to determine whether or not an organism is able to decarboxylate the amino acid ornithine. This process is called ornithine decarboxylation. Ornithine is an amino acid, and you may recall our talk about amino acids back in lecture unit 1 when we talked about translation. Amino acids are the building blocks of proteins, so it's really important and has a very important role within the cell. So on the bottom left, you see the general structure of an amino acid. You'll notice it has a central carbon, and to the left is an amine group, which has a basic pH. And on the right is a carboxyl group, which has an acidic pH. That's where an amino acid gets its name, an amine group and an acid group, so amino acid. And then you'll notice there's this R group right here, and that's going to be what makes each amino acid unique. The R group is different for every single amino acid. So if you look up here in the middle of the slide, this is what the R group is for ornithine. You notice it has 3 carbons, 8 hydrogens, and a nitrogen. And so this R group is going to be what gives ornithine its special properties. And that's going to be what gives every other amino acid its special properties. Some are hydrophilic, some are hydrophobic. Some have a positive charge, some have a negative charge. Some amino acids, like ornithine, don't have a charge. So what is decarboxylation? Well, when you're looking at the word, the prefix here is D. That means like removal of, okay, or without. So if you look at the bottom right picture, notice what decarboxylation is. It's where we're removing the carboxyl group. And in order for this to happen, there has to be a certain enzyme called decarboxylase that the organism can use to remove that carboxyl group from an amino acid. I had to adjust this slide so that the captions wouldn't cover any of the text, and I made that X look a little wonky. It's distracting. Okay, so what is going to happen is if the organism has the decarboxylase enzyme, then that enzyme, under the right conditions, will strip the amino acid of its carboxyl group. And what that does is it's going to increase the pH of the environment. Because go back to this left-hand picture, the general structure of an amino acid. Notice that it has a basic group on the left and then the acidic group on the right, which neutralizes that structure. So when decarboxylation occurs and that acidic structure is removed, then all that's left is the basic group, that amine group. So the pH is going to increase because there's going to be an accumulation of these basic amino acids. Now, how does decarboxylation actually happen? It turns out that the decarboxylase enzyme that will do the decarboxylation requires an acidic environment to work. So that means that we have to take this broth that's normally a neutral pH, because remember, most organisms are neurophiles, and we're going to have to force the bacteria to do fermentation in order to decrease that pH. Once that pH has decreased, if the enzyme decarboxylase is present, it will be able to do its job and remove those carboxyl groups from ornithine. If that happens, then the pH is going to increase again because those carboxyl groups will be gone. However, if we force the bacteria to do fermentation in order to decrease the pH to allow decarboxylase to work, if the organism does not have decarboxylase, then that environment is going to remain acidic because there's nothing there to counteract it. So that's why on this media, you notice on the slide, I point out that there's a layer of mineral oil. We add that layer of mineral oil after inoculating these tubes in order to cause fermentation to happen. So let's take this mineral oil layer conversation kind of from the top. We need an acidic environment in order to activate that decarboxylase enzyme if it's present. The only way we can get that acidic environment is if we force the bacteria to do fermentation. In order to make that happen, we add mineral oil to the tube because that creates an anaerobic environment. That prevents the bacteria from doing respiration if they're able to. So by adding that mineral oil, we seal off the media from any external oxygen, creating an anaerobic environment. In this anaerobic environment, we are forcing the bacteria to do fermentation. Fermentation releases acidic byproducts. So eventually, the media is going to turn yellow no matter what's in it, because fermentation has to happen in order to decrease the pH of the environment. Now, here's where things get a little crazy. So no matter whether we have E. cloacae or Klebsiella pneumoniae, the environment is initially going to decrease due to fermentation. So the tubes are going to be yellow because the pH indicator, bromocresol purple, is yellow in acidic environments. Now, if we put E. cloacae in the tube, it does have the decarboxylase enzyme. So once the media becomes acidic, decarboxylase is activated and it starts decarboxylating ornithine, which is going to cause the pH to go back up and the media is going to turn purple. However, if we instead had inoculated Klebsiella pneumoniae, once the pH decreases due to fermentation, there is no decarboxylase. That's not an enzyme that Klebsiella has. So no decarboxylation is going to occur. So the media is going to remain yellow because that environment remains acidic. Okay? So both tubes are initially yellow due to fermentation happening. But with Enterobacter, because decarboxylation eventually occurs, the pH will rise and that bromocresol purple indicator is going to turn purple. Okay, so purple is positive and yellow is negative. All right, that's the end of this video. Let me know if you have any questions.